This tutorial is going to be an overview of the independent samples t-test. So I'm just going to go through the same example that is in the textbook. So this is using the same data that we've had from this chapter, and so we've had a couple other tutorials that have had this same data. But just to back up, we do an independent samples t-test whenever we do a research study and we've got two different groups and we're getting a single score from each person in each group. So this is a good example of that here, or at least the way that we're going to analyze it. We've got two different groups of people. We've got people that have either been chased by a zombie before or never been chased. I'll just toggle between my values and the labels. Okay, so we've got a categorical variable where we've got people that have said that they've been chased or never chased. We've got our two different measures, our zombie opinion measures, one before they went to sensitivity training and one from after when they went to sensitivity training. What an independent samples t-test is going to allow us to do is analyze one of these variables at a time. Okay, so we can either do the zombie measure before sensitivity training or the zombie measure after sensitivity training, and we can look to see whether people that have been chased versus never chased differ in their opinion of zombies, really just on one of these measures at a time. There's more complicated or sophisticated analyses that you can actually look at all three variables. That's actually a mixed design. You might remember that from chapter 1, where we look at essentially like a repeated measures design or within subjects design, so time 1, time 2, and then we've got a between subjects design, and so we can look at whether the change from time 1 to time 2 is consistent for people that have been chased versus never chased. But that's a very complicated analysis and complicated interpretation. What we're going to do is just a simple version where we're just going to look at one variable at a time, so one of these dependent measures at a time, and simply ask, on average, do people who have been chased versus never chased have a different opinion about zombies? Okay, and so this is appropriate for all kinds of like real life research scenarios. So in psychology, we do experiments, and so a very simple research design would have like an experimental group and a control group. And then we get some score or some measure from each person in the experimental group and each person in the control group. And then we just compare, are the scores different between the experimental group and the control group? That's an independent samples t-test. Alternatively, you could just compare pre-existing groups when there's two pre-existing groups, like men versus women, okay? Republicans versus Democrats. So when we have two groups and we get a single score from each person in the group, we do an independent samples t-test. This is how we do it in SPSS. We go to our Analyze menu, Compare Means. This should be pretty familiar by now. This is now the third time we've gone through this menu. And then we've got Independent Samples t-test. Okay, so this is our dialog box. I already set it up. Let me reset that. So here, let's just get the variable names. That could be easier to look at sometimes. So we've got our two zombie measures, so time 1, time 2. And I'll just put one in. Okay, I just highlighted it and I moved it over with my arrow. And then our grouping variable is going to be our categorical variable. So this is the chased variable. I'll move that over. Now what you'll see is we got these question marks. We have to go into our define groups but dialog box here. So it says use specified values group 1, group 2. This is where we need to use the numerical, this is where we need to use our values, our numbers. So we can't write, I'll just do it so you can see, but if we write chased, I don't know if you can hear that, you can't even enter anything. I'm trying to press the C button, okay? But you can put a number in. So this is where you have to remember, let me just cancel real quick. This is where we have to remember what numbers we used to define our groups. And that's the main reason is SPSS needs those numbers. All right, so I'll go back in. Just almost wanted to demonstrate what it's like to have a little bit of error on this part, something that you might encounter. Okay, so analyze, compare means, independent samples t-test. Okay, I'll reset the whole thing. We'll start from scratch. It's easier to see the variable names sometimes. I'm just going to do one at a time. I can do both, actually, okay? But I'm only going to do just this one. Chased as the grouping variable, move it over, and then define groups, okay? So now I can look and say like, oh yeah, now I remember one of my groups I defined as 1 and the other group I defined as 2, okay? Now, it just so happens that I'm putting 1 for group 1 and 2 for group 2. You don't have to. You can do 2 and 1. You can do it that way if you want. I might show you later on just how to do it both, you know, what the difference is, okay? It also just happened that we defined groups, or the textbook authors defined their groups as 1 and 2. You don't have to be 1 and 2. It can be 0 and 1. It can be 2 and 3. It can be 4 and 5. It doesn't really matter. SPSS is flexible with what numbers you use, so long as you use numbers to define your groups. All right, and then that's it. We don't really do anything with the options. The only option that we really have is to specify our confidence interval. By default, we use a 95% confidence interval. And then we have to tell SPSS how to treat missing values, but we don't have any. So we can either just continue or cancel. Okay, the Bootstrap option we don't use. This is by default, there's an estimate of effect size. I don't have you do anything with this. It would probably be better if I did for this lab assignment, but I don't. So we'll just go ahead and paste that. There we go. Here's our syntax for us to save for later. Play the syntax. So really, it's pretty easy to generate the output. The harder thing is interpreting what the output means. So the first thing is SPSS provides us with our descriptive statistics for each group. So we can see ever chased by zombies, and so this is chased and never chased. And if we didn't have our labels here, so I'll just show you. Recall that in variable view, we specified labels, okay, where 1 is chased and 2 is never chased. If we hadn't done this and we only had 1s and 2s, that's all that would appear in our output. We just have a 1 and a 2 here. So it's beneficial to put in your value labels so we know kind of what group we're talking about. This is the label of the, I guess I'll show you that again too. Sorry, going back and forth. But you'll notice that that's what's showing up is the label for our variable. So our variable is named zombie, but our label is zombie opinion measure form B. So this is why it's nice to put the labels in, is because the labels will appear in SPSS. If there's no label, it will just default to the variable name. So if we didn't have zombie opinion measure form B, it would just say the zombie name right there, okay? And then you get like a 1 and a 2. So the labels are nice, all right? But what we get is we get our sample size for each group. So 14, and it's 14 for chased, 16 for never chased. It is not a requirement of the t-test to have equal sample sizes. You can have unequal samples. We get the mean for each group, the standard deviation, and then the standard error of the mean. Okay? So again, recall that a standard error of the mean tells you that as an estimate of the population mean, that's about how much we can expect this sample mean to be in error of the true population mean. Right? The standard deviation is literally among these 14 scores, what is the average deviation from the sample mean? Well, actually, this is, to be a little bit more precise about that, it's an estimate of the average deviation from the mean at the population level. So it's not literally at the sample level, but we can say about how much do we expect people to differ from this mean on average in that group. Okay, the next part of the output, and this looks just ever so slightly different than what is in the textbook, this table, because it's all smashed together. One of the assumptions for the independent samples t-test is that our samples come from populations that have an equivalent amount of variability. That is, the variance in each of the populations from which these samples are drawn have equivalent variance. So it is an assumption of the t-test. And so that's what this Levine's test is for, to test whether or not this assumption has been violated or not. So this is one of these rare instances in statistics where we actually want a non-significant result. Because what a significant result tells us is that the assumption of the test has been violated. Okay, so this is written up in the textbook. I think you can find it somewhere around page 100. Okay, so what we're looking for here is, you'll notice that there's two different lines in the table. There's two different t-tests, two different degrees of freedom, two different significance levels. What this Levine's test, this is kind of like a first stopping point, or a first checkpoint, because depending on whether or not this test is statistically significant or not, that will determine whether we use the top row in the table or the bottom row in the table. Okay? And again, it's somewhat counterintuitive, but we actually want this result to be non-significant, because what that means is that we do not have a violation of the assumption. So this really tests, it's called the Levine's test for equality of variances. It should really be called the Levine's test for inequality of variance, because if you get a significance test, it means that the variances are not equal. Okay, so anyway, what we have here, recall that our test of statistical significance is we're looking for a number that is either greater than or less than 0.05. If the number is less than 0.05, we do have a statistically significant result. And if the number is greater than 0.05, we do not have a statistically significant result. So what we have here is a significance level that is more than 0.05, so we do not have a statistically significant result. Basically what that means is that the two variances are not statistically different. The two variances in the population are not statistically different, and that's actually what we want. Okay? So because the two variances are not statistically different, we can assume that the variances are equal. Okay? So whenever we get a non-significant result here, we will use the top row. If this number is less than 0.05, or I believe your textbook authors want you to use a number that is less than or equal to 0.05, that's a matter of contention, but that's fine. So less than or equal to 0.05, we'll use the bottom row of the table. Because what that would be saying is that, yes, there is a statistically significant difference between the two variances, so I have to assume that the variances are not equal. And then, there's basically an adjustment to the t-test formula that's done. Lucky for us, and I believe this will be the case in your lab assignment as well, you're most likely, I don't quite, to be honest, I don't remember what I did, so don't turn off your brain, look at this number. Okay, but if this is a non-significant number, use the top row. If it is a significant value, use the bottom row. All right. Then what we can do is we go to the statistical significance of the t-test. Okay, and so you'll see that there's two significant values. One is for the f-test, which is a test of assumptions. The second is actually a test of whether the means are different. So same thing here. We're looking for a result that is 0.05 or less. And we see in any event, it would be whether we have the assumption that is violated or not. So what we can see is that our test is telling us that there is a statistically significant difference between the means. Okay? What that actually means is that at the level of the population, this is telling us that the means in the population are different. We know these sample means are different, right? Like 7 is different than 12. Those are different. So why do we need to do a test of that? Because what our test is actually showing is that those means are different enough to reject the null hypothesis that they're sampled from populations that have equal means. What we're saying is the means of the populations from which they are sampled are different. So different at the level of the population. Okay? Population mean 1 is not equal to population mean 2. That's what this is telling us. It's not telling us that the sample means are different. It's telling us that the population means are different. All right. So yes, we have statistical significance here based on this t-value. The mean difference is just group 1 minus group 2. So we get a mean difference of negative 5.32, etc. because we took we didn't, but SPSS took 7.42 minus 12.75. The standard error of the difference is a statistic that tells us, just due to random sampling error, about how different would we expect any two means that are sampled from populations based on a sample size of 14 and 16, about how different, even if they're sampled from populations that do have the same mean, about how different might we expect the means to be just via random sampling error. So what the standard error of the difference is telling us is that if our sample means were different by about 2 points, that would be about what we'd expect on average. Because our actual mean difference is 5.32, we say we can evaluate that mean difference in terms of what we expect ahead of time. So our t statistic is the actual mean difference that we observe over the standard error of the difference. So we get negative 2.614 by taking negative 5.32 and dividing by 2.03. Okay, so you can think of the t as this ratio of how much actual difference did we observe between the means over how much did we expect there to be ahead of time. And so when this t gets big, it just means that there's a lot of difference between those two means in comparison to what we would expect there to be just because of random sampling error. All right, maybe more information than you really needed to interpret the statistical significance, right? You can just kind of do the binary decision. Is this less than, is this 0.05 or less? Yes, it is. Okay, statistically different, right? But why is that the case? A little bit of a deeper explanation for you there. Okay, now what about this confidence interval? This confidence interval is telling us what the true difference between the means at the population level is likely to be. So what this is saying is that the means can be as different as 9.49 points. So in other words, people that have been chased could have a mean in the population that is 9.49 points lower than those that have never been chased. Okay, although it could be the case that that difference is only as big as 1.15 points. Okay, so the difference between the opinions of people that are being chased versus never chased, we found to be 5.32. But that's not necessarily the true difference in the population. That's our best guess, but it's not necessarily the true difference in the population. The true difference in the population, or among these populations, could be as large as negative 9.49, or it could be as small as negative 1.52. Okay, so in other words, the chased group could have a lower opinion by 9.49 points, or by only as much as 1.15 points. Notice, however, that that confidence interval does not contain 0. Okay, meaning that we can be 95% confident that there is at least some difference between these two groups in the population. Okay, so it doesn't, this 95% confidence interval does not contain 0. Anytime you have a statistically significant result, a difference between two means, you won't see 0 in this interval. Okay. All right, I think that's actually about all I want to say. So again, the most important thing is, it's fairly easy to run the test, but the most important thing is to be able to interpret the output. The descriptive statistics tell us the difference between the two groups in terms of who has a higher score versus who has a lower score. The statistical significance will tell us whether that is a statistically meaningful difference, as in there's likely to be a difference between the means in the population. Okay, and in this case we say yes, it is. So these means are statistically significantly different, which means that these two samples are likely drawn from populations that have different means. The reason that we interpret this top line instead of the bottom line is because our Levene's test for equality of variances was non-significant. That's actually what we want. This is telling us that the variance is not different between our two groups. So equal variances can be assumed. And then our 95% confidence interval is giving us the range that we could, of difference that we could expect. So it's saying at a population level, the population means could be as different as 9.49 points, or they could be still as different as 1.15. This would be the largest it could be. This would be the smallest it could be. All right. Hopefully that was informative. You know more about how to interpret an independent samples t-test as well as some of the conceptual basis as well.